Well, thank you, Cassie, for the introduction, and thank you all for attending Swine Day. We're very excited to be in person again this year, and this is my first opportunity being on faculty to actually present at Swine Day in person. Was able to participate in our virtual offering last year, but very excited this year to speak to the audience and interact with everybody today. So in the second half of our presentation here today, I'm going to focus on some of our recent data, focus specifically on this concept of minimization as well as mitigation. I want to spend just a few brief moments talking and further describing some of our data which we were able to work with a collaborator located in Vietnam and help understand what was the risk of certain surfaces within their feed production system for becoming contaminated with ASF. In Vietnam, during this project, was very much being affected by ASF and disseminating and distributing through the region. So within the feed system, with over 2,000 samples collected, overall we only had 17 PCR positive samples. And when we look at the distribution of the breakdown of where these samples came from, over half of them were either on feed trucks or the people themselves within this feed mill. And one of the key findings of this research was that people in trucks are really, really important to consider within our biosecurity programs. And that's not rocket science, it's nothing new. We know that concept and we've known that for decades, but the data helps really illustrate it even with a very, very impactful disease like ASF, understanding people and vehicle movement is critical. So here is what this data looked like specifically in terms of feed delivery vehicles. Along the horizontal axis is the sampling month that we collected samples. The bars represent the number of samples collected within each of those respective sampling months. The numbers at the top of the bars represent the number of PCR positive samples within each of those. You can see that in total, within these feed delivery truck samplings, we only had 7 PCR positive samples. And all of those were within the first 2 months of the investigation. So this was very eye-opening for this production system and helped them to recognize that, hey, feed trucks are a huge limitation within our current biosecurity programs. We need to do something differently. They implemented changes, and as you can see thereafter, we found no further evidence of contamination of these trucks after these changes were implemented. So what are these changes? What did they do? We know that it's relatively easy to clean the outside of trucks. You can pressure wash, dry it, add the disinfectant of your choice as long as it's appropriate and effective concentration and effective contact time. It should work well. However, the data illustrates that the inside of truck cabs is a huge area of concern, and when you're leaving today on the way home or wherever you're headed after today's event, open up the door of your vehicle and look around. Would it be very easy to sanitize or disinfect the seat, the floor mat, the steering wheel, the radio dials? A cab is a pretty complex series of different surfaces that's really difficult to disinfect. So what the data illustrated and what they did here was they actually took a backpack leaf blower, they mounted a disinfectant tank, and they would use that to fumigate the inside of the truck cab. Now again, as you're leaving and looking at your vehicle, we probably wouldn't want to do that with many disinfectants on all those surfaces. However, in an area of ongoing ASF circulation, extreme times call for extreme measures, and in this case, the data very clearly indicates it was quite effective. So we wanted to follow that up, and this was a research project that Dr. Grace Elijah, or Dr. Grace Houston after she got married last weekend, worked on and within our feed mill here, within our BSL2 space, where we took real full-size semi-truck cabs that we found in a salvage yard in Beloit, Kansas, brought down here to Manhattan, and we brought 3 of them into our facility. And what we did was we used PDV and PRRS virus, so 2 endemic viruses here in the US. We mimicked a number of different surface types within these truck cabs, fabric, rubber, and plastic, and then we evaluated a series of different ways to decontaminate those surfaces. We had a none-control treatment, so we didn't have any disinfection treatment, or we used a series of different disinfectants such as Synergize, Intervention, or a very, very high concentration of bleach at a 10% dilution, and we applied those either through a hurricane fumigation system, which creates a small particle-sized droplet that fills an airspace, a handheld pump sprayer, or we also evaluated an extended downtime, so letting that surface sit for 10 hours prior to sampling. And the rationale for that was we found a commercially available commercially available product which produces and creates a chlorine dioxide gas that fills an airspace. And what we are interested in with that is, can we help remove some of the human element? I would imagine that with a handheld pump sprayer, the efficacy of that disinfectant step is highly dependent on the person applying it. How much did they apply? Did they get good, even coverage on all those surfaces? So the goal with this product was to help eliminate some of that human aspect and help standardize this process. So along the x-axis of this graph is our different treatments. With the no disinfectant treatment, those disinfectants applied to the hand pump sprayer or the hurricane fogger. And in the vertical axis is the percentage of samples that were PCR positive. Or in other terms, looking specifically at, can we find the RNA of this virus on that surface? It doesn't tell us, unfortunately, whether or not that virus is intact and can cause infection or not. And what we see is that if we look specifically at fabric, plastic, or rubber surfaces, we oftentimes can detect the virus, or the RNA at least, on that surface. Again, we need to understand this further in terms of, is that material able to cause infection or not? But one of the important findings of this project that expanded into a small follow-up project was that we found that if surfaces have organic material present, dirt or feces, it greatly reduces our ability for this environmental sampling technique to find that virus. So the goal of this project was to help understand how can we optimize our sample collection and sample analysis procedures to make sure we find the virus if it is in fact present on that surface. So what we did within this project was we had 4 levels of contamination. We had pure virus, we had virus diluted down with PBS only, or we had virus inoculated with dirt, feces, or the combination of dirt and feces. And within this, we had 4 different ways of collecting and preparing these samples for the PCR analysis. We did our standard swabbing procedure, which is simply taking 4x4 cotton gauze surgical sponges, pre-moistening them with PBS, wiping that on the surface, putting it into a tube, adding a little bit more PBS to dilute it down, and then taking off that liquid for PCR analysis. We followed that up, and once we take that sample off, we would then centrifuge that sample to spin down any debris that may remain in that sample, or we took that sample and passed it through a syringe filter in the laboratory, or we did a combination of both centrifuging as well as using the syringe filter. Along the horizontal axis are our types of inoculations: pure virus, virus and PBS, or virus with differing amounts of organic material contamination, either coming from dirt, feces, or the combination of both. And then the vertical axis of this graph represents the percentage of samples that did in fact contain PEDV RNA. And in this example, when we're trying to optimize our detection and optimize our diagnostic sensitivity, a higher value or a taller bar is better. So when we look at the no processing, which is just our normal sampling procedure, with relatively clean samples, low levels of contamination, works pretty well. We can find that viral RNA. However, when we get to dirty samples, we see a significant and substantial reduction in our ability to find that virus on that surface. However, if we centrifuge that sample prior to the PCR analysis, we see detection 100% of the time. And again, a higher level of detection, a taller bar in this case, means that procedure is better suited to detect that RNA. And we see similar results with syringe filter, except we see poor efficacy within the high levels of organic material presence and somewhat intermediate with both the combination of centrifuging and filtering. So what this illustrated for us is that if we collect environmental samples, we surely should be centrifuging those prior to PCR analysis in order to make sure we can increase our chances of finding that virus on that particular surface sample. So what this study indicated was that organic material can reduce our ability to find a virus on a surface, but if we centrifuge it, we can greatly increase that chance. And additionally, not only this study, but some of the other work our team has been working on recently has indicated that when we send these samples to the diagnostic laboratory, generally they have a cycle threshold cutoff, which they go up to that point for clinical samples, and then after that, if they don't detect any viral RNA or DNA, depending on the type of pathogen they're going after, then they say that sample does not contain undetectable levels. However, you can ask the lab to take that to a slightly higher level, and there's some pros and cons to that. The advantage from what we found from several of our studies is we can increase our chances of finding it if it's there. The downside is the repeatability. If you run that same sample again, it may not give you the same answer, which makes, or in other terms, can greatly increase our chances of having a false positive test result. However, then it becomes very important how you use that information. If you're using this sampling and this diagnostic testing to help identify biosecurity gaps, we want to do everything we can to find positives if they are in fact there. So this is one way that we would recommend to do that, and if any further questions on that or discussion, feel free to find any one of us and we'd be happy to visit more about that. So next I want to talk about Glo Germ. So Glo Germ is a visual training aid which we think is very useful to help train and help implement and reinforce the importance of biosecurity within our swine production systems. So this was an example at our KSU farm where Olivia did a nice job in conjunction with Cassie's undergraduate research course to evaluate the efficacy of certain biosecurity measures, including an entry bench as well as our entry shower. The graph represents the change in coverage on this floor surface, either before compared to after approximately 30 undergraduate students passed through that material. And what we can see is that if we don't have any biosecurity measures in place, we see an increased coverage of Glo Germ as we would expect. However, in this example, both the entry bench as well as shower did in fact show ability and efficacy at not allowing that surface to become covered with Glo Germ, certainly as we would expect. But one of the nice things about Glo Germ, and here's a before and after image. So this is the flooring just past the inside of the shower. So we should have showered in, should have gotten everything off of us, we should be clean. The fluorescence you see here is just artifact based on the flooring. However, in the after image, you can see the clear orange fluorescent powder, which the nice thing about this is that you can use that as an education tool. Take a picture of that, visit with the undergraduates and any other personnel coming and going from the facility, and help illustrate the importance of biosecurity and how we can have pretty clear evidence that we have room for opportunity within those biosecurity practices. So I followed that up and a few weeks later, and the grad students probably were a little bit mad at me afterwards, or AJ specifically, but what I didn't tell them is that the night before one of their way days out at one of our facilities here, Olivia and I went out and sprinkled some Glo Germ on the sidewalk. It may look like rock salt or any other white powder, but at 5:30 in the morning you don't notice that. But what we see is on the dirty side of our entryway, we see a lot of Glo Germ powder, as we would expect. They're just coming into the facility, they haven't used the entry bench yet, and on the opposite side of the entry bench, you can see there's relatively little fluorescence. However, this is on the clean side of the entry bench, and what you see is a very clear footprint, and when we look a little bit closer, you can see that footprint matches up with the bottom of a crock that are used to walk between buildings on the dirty side. So this is just a great example, even here at our facility at K-State, not to take it and identify who it was and crack the whip and anything like that, but help illustrate the importance of biosecurity and how we can continue to reinforce these practices that can be implemented on a daily basis 100% of the time. So now we'll talk a little bit about cross-contamination and briefly highlight some of the recent work we've been doing with ASF here at K-State. So within the Biosecurity Research Institute here on campus, we conducted a study where we inoculated batches of feed with ASF. We then followed those subsequent batches of feed to determine the cross-contamination within those subsequent batches of feed manufactured after that positive batch. The samples collected before we inoculated with virus did not contain ASF, as we would expect. However, after we mix ASF into the virus, every subsequent batch of feed contained ASF DNA. So what this really illustrates is clearly that once contamination enters a facility, we can see quite substantial crossover into subsequent batches. And when we take that beyond just looking at feed samples, but now looking at surface samples, we see that the feed contact surfaces, about 40 to 80% of those surfaces have detectable ASF DNA after the time of feed manufacture, after each of those batches. And we see similar trends for non-feed contact surfaces, both in close proximity, less than 1 meter, or slightly further away, greater than 1 meter from those feed contact surfaces. And when this gets interesting is that if we look specifically at the shoes, the soles of researcher boots, once we inoculate that batch of feed within this facility, Every time we swabbed a worker boot thereafter, every single one of those samples was PCR positive. Again, further illustrating the importance of people and people movement within the transmission of this virus. So not only did we analyze those feed samples on the day or shortly thereafter making feed, we also stored those samples at room temperature at up to 180 days. And what we wanted to know here was, what was our ability to detect ASF DNA even after an extended period of storage? So what we can see is that on day 1, 3, 7, all the way out to 180 days of storage at room temperature, and those early batches of feed, we can still find a large amount of ASF DNA in those samples, even after 6 months. We see a little bit more variability out with some of those later batches of feed, and generally we believe that's because they have slightly lower levels of ASF presence in the beginning, so that can lead to more variability in detection throughout that storage period. But in general, the data indicates that even after storing feed for 180 days, if ASF was in it, we're still going to at least find the DNA of that virus. Again, by no means tells us if it's infectious or not, but from a sampling and detection standpoint, ASF DNA appears to be extremely stable in feed over time. So with that, I'd like to, and again, repetition is the key to memory and interpretation and implementation, right? So the concepts of exclusion, minimizing, and mitigating not only apply to ASF, but really apply to about any pathogen we can think of. PED, any other virus, many bacteria as well. So really the concepts that Cassie began to outline and then we talked a little bit further about really apply to anything and are really, really important to consider within our swine operations. So along with that, just to wrap up here, focusing and looking specifically at the mitigation piece, I want to highlight a new resource that was recently put on our KSUfeed.org website. And again, I'd like to highlight that website as well. We have our www.ksuswine.org website, but also, and we had a feed safety resources tab within that, but now we have a standalone feed safety and feed science tab as well, www.ksufeed.org. And those are both cross-linked, and this material and this resource is available on there as well. So what we did was based on a number of questions with producers and different nutritionists and different folks, asking the question of what products are on the market and what data would be there to support potential reduction in viral survival or viral stability in feed or in ingredients over time. So what our team did was to work with various suppliers to capture and gather any data that they would have available and information regarding pricing and contact information, put all that into one document to help producers sort through, navigate this area, and help put all that information in one place. So this resource is available on the website and would encourage anyone with interest to look and take a look at that a little bit further. So to wrap up, and Cassie started talking, began the session talking about some of the regulatory implications, and then we talked a little bit more about the science and data, and to wrap up with where we see this moving forward, this feed safety area as a whole. So we've learned a lot in the recent months about where various products are coming from and where coming in and bringing into the U.S. in terms of imported products such as soy products and many others. And we've learned what some other countries are doing in this area. Australia or Canada, how are they handling this risk? What measures are they putting in place? So one of our future steps with this area, and Dr. Main will talk about the U.S. swine improvement plan in the next presentation here, but our goal and our plan would be to help contribute to that and help provide some guidance by leading a working group focused specifically on feed biosecurity to help take some of the science, translate that into guidance and recommendations for the industry moving forward. So with that, I'd like to thank Cassie, Jason, Chad for the ability to work together in this area and work in this feed safety area. I'd like to thank our collaborators. Dr. Jürgen Richt and his team have been very instrumental in the ASF research. Dr. Roman Pogranichny in the Kansas State Veterinary Diagnostic Lab, as well as Dr. Bai. Always very supportive of our projects and certainly grateful for that collaboration. And then finally, I'd like to wrap up, and this is the last of the scientific portion of today's event. So I'd like to take an opportunity in the feed safety side to thank our graduate students, Allison, Olivia, as well as Grace, but not only to wrap up for all the students as well. So if I could take a moment and have all the current graduate students please stand up. If everybody could help me and thank them for all their hard contributions throughout the year. You guys are really the ones with 55 papers, 53,000 pigs on test. The students are the ones that make all of that happen. So thank you for all your hard work throughout the year. And with that, I'd like to wrap up and we'll transition back to Joel for the introduction of Dr. Main.